Hi, in this tutorial we will continue with the study of the computation of the closure of F or F plus. And in our previous tutorial we were studying the Armstrong's axioms that we will use to derive new attributes. So we will solve now this exercise. So here it says we'll use Armstrong axioms to show that if we know this, so this is what is given, then this logical implies this. So then, as we did in the previous tutorial, we write statements until we reach this conclusion. So the initial statements are what is given. So basically what we're doing is giving names, like this is statement 1, statement 2, and statement 3. So we say A implies C, something that is a true statement because this is given. Now my second statement is that B implies D, and that is given. My third statement is that C and D implies E, and that is given. So now I use the statements that I know and the rules, the Armstrong's axioms, to eventually reach this conclusion. And if we do, then this is true. So something that we can say as my fourth statement is that, for example, if we do the B in both sides, that's the augmentation rule. So we can say A and B is the same as CB, and this is by rule 2 on 1. Now my fifth statement, I can add the CB in those two sides, and then we can say that CB implies CB, and this is by rule 2 on 2. Now we can do transitivity because we can say A implies CB and then CB. Here we can say AB implies CD. So that would be my sixth statement. So AB implies CD, and this is by R3, which is transitivity on 4 and 5. So this is my justification. Now CD implies C. I can do another transitivity. So that will be my seventh statement, that AB implies E because CD implies E. So this is by R3 on 3 and 6. And this is what we wanted to prove. So we're done with that exercise. Okay. Then if we continue with the computation of F plus, um, so we have ways of uh, using the Armstrong axioms, but then we also have something that we call the closure of attributes. So that means that um, to determine if actually functional dependencies can be implied, we could just compute the F plus, and then if this is an element of the F plus, then it is uh, it is true that can be implied. Otherwise, it isn't, it cannot be implied. But we have the problem that computing the F plus is very expensive. So that means expecting in the time of computation. So there is another method that says that we do the closure of the attributes under F. And for that, we're going to have the following algorithm that will I will illustrate with an example. So the algorithm says that the input that we need is a set of functional dependencies that we call F, and the set of attributes X, and then the output will be what we call the F plus. That means all the attributes that can be derived from that, and we will have basically a loop in which we'll go in for every functional dependency uh, in the set. if y is a subset of that x plus, then we add those elements to the set and we continue that until we don't see any change. So I've illustrated that with an exercise. So let's do that. And this is the exercise that we're doing. So we have an example in which my relation has the following: is an A, B, C, G, H, and I. And my set F is A plus B, C, G plus H, I, B implies H, and A implies C. And the question is, compute AG plus. I mean the closure of those attributes. Don't confuse that with the F plus. F plus will be all possible functional dependencies that can be derived. So then this is what we do. We initialize and then we said, okay, AG plus. So initially is the same elements that are here. So this is A and G. And then the algorithm says, we go for every functional dependencies that is here, and then if this is a subset of this, then we union. So for example, A is a subset of AG. Then we add this side, which is B. So I'm adding B. There is a change, right? The initial value was AG in this iteration. Then now I go with the next functional dependencies. Is C and G a subset of this? No. Is B a subset of this? Yes. Then we add H. So we got H. And we go with the next one. Is A a subset of this? Yes. Then we add C. We stopped that in the iteration. There was no change. But there was a change from the initial iteration. Why? Because we started with AG. So then we do it again. So now is A subset of this? Yes. Then we union with B. There is no change. Because remember, we don't have any repetition in sets. Is CG a subset of this? It is now. So we add HI. So H is already in the set. So we're adding I. And is B a subset? Yes. And I think we got all attributes already. So this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there is nothing else to add. So that will be the AG class. And we conclude because we continue with that, well, eventually will be no change because there is nothing else to add. But now this is a good point to make an observation. Look, these two attributes derive the value of all other attributes. Then this is also a superkey, right? Because this derives the others. So there will be cases that we will also find keys. Now, we wonder, is this also a candidate key? So this wasn't part of the exercise, but we said A, G is a superkey. Why? Because we see that these two attributes together derive all other attributes in the table. Now, how do I know that this is a candidate key? Candidate key will be the minimum combination of attributes in this case that will hold the property of key. So for example, if I take away the A, G is no longer a key. If I take away the G, A is no longer a key. If if one of them is a key by itself, then this is not a candidate key. So let's see. To do that, we check the A plus. I mean, it wasn't part of the exercise, but now let's do this. A plus. So A plus, we start with A. And then A, we're going to check, give us a B. And then is this a subset? No. Is this a subset? Yes. We got the H. Is this a subset? Yes. So the C was a change? Yes. So we iterate again. So is this a subset? Yes. The B. Is CG a subset? No. B is H. A. There is no change. So is this a key? No. So that means A by itself is not a key. So let's check if G by itself is not a key. So not a key. So G plus, we start with G. Is this a subset? No. Is this a subset? No. Is this a subset? No. No. So G plus is G. So not a key. So what is the conclusion? A G is a candidate key. Why? Because A is not a key, G is not a key, and when we put them together, they're a key. So it is a candidate and it's a superkey. Okay, so that will be all for this tutorial.